This lesson is about the trigonometric form of complex numbers. And at this point, you've probably worked with complex numbers from time to time and have seen at least how they can be used as solutions to equations involving square roots of negative numbers. Now we are going to explore them from a graphical point of view so that we can learn more about performing the basic operations on them more easily. Real numbers only need a one-dimensional number line in order to graph points. So for example, if I wanted to graph the point x equals 2, I have a number line and the point x equals 2 is right here. I could fill in a circle and plot it. Complex numbers, on the other hand, if we want to graph a complex number, which is of the form z equals a plus bi, we need a two-dimensional plane so that we can plot the real part on the x-axis and the imaginary part on the y-axis. So for example, let's graph the following. Here is the axis I'm going to graph these on, and I'm going to label the x-axis as my real axis and the y-axis as my imaginary axis. So when I want to plot the point z equals 2 plus 6i, 2 is the real part of that complex number. So I go 2 in the real direction, and then 6 is the imaginary part, so I go 6 in the imaginary direction. And here is my point. So point A, which is 2 plus 6i. B is the point z equals negative 8 plus, or negative 8 minus 6i. So I find negative 8 on the real axis and minus 6i on the imaginary. And wherever those two intersect, that's point B, which was, of course, negative 8 minus 6i. If I label this one, this was 2 plus 6i. C is z equals 3i, so that's only on the imaginary plane, so or the imaginary axis, I should say. So I'm going to go 3 in the imaginary direction, and right there is point C, which is 3i. And we can still plot real numbers on the real and imaginary plane. Everything just basically comes down to a real number line. So a completely real number, there's no imaginary part, would just end up right here on the real axis in the same way that we would have plotted it on a one-dimensional number line. So this is point D, which is at negative 4. Since these values fit naturally on a two-dimensional plane, we can treat them like vectors, which means we can express them in both rectangular and trigonometric or polar form using the following transformations. So if I have a point a plus bi somewhere in the real and imaginary plane, a is the distance that I've traveled in the real direction, b is the distance that I've traveled in the imaginary direction. So that particular point can be labeled also using distance from the origin and an angle measure as well. So we can use the transformations that we learned earlier. X equals r cosine theta, y equals r sine theta, r equals the square root of x squared plus y squared. And actually, the thing that I have listed as a z here is what I'm referring to as r in this situation. And tangent of theta is y over x. So we can express these complex numbers in both rectangular and polar form. So the trigonometric form of complex numbers, let's look into that in a little more depth. If we use these transformations to make some substitutions, we can arrive at z equals x plus yi. That's our starting point. So x is the direction that we move in the real, y is the direction that we move in the imaginary. Using our transformations, so I have x equals r cosine theta, y equals r sine theta. I can substitute in as such. Now if you'll notice, there's a factor of r in each one of these, and I could factor that out and express my my value this way. And it turns out that this statement right here, we have a way of expressing that. It's the expression CIS theta. So CIS theta is equal to cosine of theta plus I times the sine of theta. It's just a shorthand notation for that representation. So instead of copying the angle measure theta twice, you can just write it one time. It's much easier. It's not actually the standard method of expressing complex numbers in trig form. There is a different way. And if you go into a more advanced complex methods class, you'll learn that other way. But for now, this is pretty much a standard for trig classes. So this is called the trigonometric form of complex numbers. So let's convert the following numbers to trigonometric form. Starting with z equals 4 plus 4i. And I'm going to also plot it so we can kind of get an idea of what's happening here. So 4 plus 4i. So that's 4 in the real direction and 4 in the imaginary direction. So my point is right here. This is my value z, 4 plus 4i. Now, I had to come over some distance in the x and up some distance in the y, which makes a right triangle, so that this angle measure, or this distance right here, is r, the distance from the origin, and then I'll label this angle as the angle measure theta, the amount that we've rotated from the x-axis. We need to figure out what r and theta are. To do that, we use the formulas. R equals the square root of x squared plus y squared, so 4 squared plus 4 squared in this case. So 4 squared is 16, so 16 plus 16 is 32, and 32 could be written as 16 times 2. 16 is a perfect square, so I could actually factor out a 4, and that would leave me with a square root of 2. So that is the radius. The angle measure theta is going to be the arctangent of y over x. So y is 4, x is 1. Because remember, these are always of the form z equals x plus yi. X is the real part, which is the x-axis. Y is the imaginary part, which is on the y-axis. So this is the arctangent of 1, which you could get your calculator out, but you probably recognize at this point is 45 degrees. So what that means is I can express this number in trigonometric form as z equals 4 square root of 2 CIS 45 degrees. So that just tells me that my radius, the distance from the origin that is 4 square root of 2, and theta, the direction from the origin, is 45 degrees. I would still land at this particular point. So I can express it 4 plus 4i, or as 4 root 2 CIS 45 degrees. It's the same either way. Okay, one more example. B, z equals 1 plus I root 3. So I'll plot it first. All right, so 1 on the real, the square root of 3 on the imaginary. And the square root of 3 is approximately 1.7 if I'm not mistaken. So I'll just approximate it as best I can. So there's... Alright, so the number of tick marks that I have, let's see, this would be 1.2, 1.4, 1.6, 1.8, so somewhere halfway in between there is 1.7. So I'll just approximate it to right there. So this is z equals 1 plus I square root of 3. So I'm looking for this distance right here and that angle measure right there. Let's see what they are. So r is the square root of x squared plus y squared. So 1 squared plus the square root of 3 squared. Or the square root of 1 plus root 3 squared is 3. So square root of 4, which is 2. Theta is the arctangent of y over x. My y value is the square root of 3, x value is 1. And in order to determine this, one thing that I like to do is just recognize, tangent being the value of sine divided by cosine, try and come up with the values of sine and cosine that are common that would divide to square root of 3 over 1. So that would be root 3 over 2 divided by 1/2, because the 2's in the denominator cancel each other out. But these are the common values that you run into with sine and cosine, which you should know between 0 and 90 degrees, these different common values. But if you don't, take time to make a unit circle and just make sure you get the correct value of these, because there's no reason to get wrong answers. So we're looking to where sine is root 3 over 2, cosine is 1/2. That's going to happen here at 60 degrees, or pi over 3. Generally we work in degrees here, but just follow the instructions in your homework. Alright, so I have r and I have theta. So now I can say that this right here could also be written as 2 CIS 60 degrees. In this next example, we'll convert the following numbers to rectangular form. So for part A, I have z equals the square root of 2 CIS 225 degrees. So effectively, what we would need to do is just say, right, x is equal to square root of 2 cosine 225 degrees, and y is equal to the square root of 2 times the sine of 225 degrees. Because, of course, CIS stands for cosine times I sine 225 degrees. So we're going to get the individual x and y rectangular components first, and then combine it all together into a new rectangular form complex value. All right, to figure this out, if you aren't sure exactly what cosine and sine of 225 degrees are, just draw yourself a nice, you don't need the whole unit circle here, just one angle is all you need. This angle measure is going to be in quadrant 3, because quadrant 3 begins at 180 degrees and goes up to 270 degrees. Just had 225 on my mind. All right, and if you want to know the reference angle, which is nice, the reference angle would be 225 degrees minus 180 degrees, and 225 minus 180 is 45 degrees. So what that means is I can draw in a triangle here that has a reference angle of 45 degrees. And that reference angle I can use to come up with the values of sine and cosine. So the values of sine and cosine here would be square root of 2 over 2 for both of them, because sine of 45 is root 2 over 2, cosine of 45 is also root 2 over 2. The only thing we'd have to do then is just adjust for the quadrant. So this angle here, all the way from the x-axis, would be my 225 degrees. With that including, the only thing that changes is both of these happen to be negative. And you can also get that from all students take calculus, that sort of thing. All right, so that means x is going to be effectively the square root of 2 times the negative square root of 2 over itself. And actually an easier way to work that out, I'll just come over here to the side. Instead of saying square root of 2 over 2, if I change this into just 1 over the square root of 2, then this is effectively square root of 2 times 1 over the square root of 2, which is just going to be just 1, which is nice. So when I take square root of 2 times root 2 over 2, I get, in this case, negative 1, because there's a negative involved. And same thing happens for sine. This is going to be square root of 2 times negative, you can think of it as 1 over root 2, if you like. Either way, you get negative 1. So my x and y components are both negative 1, so that means z can be also expressed as negative 1 minus I, because the rectangular form is of the form z equals x plus I times y. So that's what I've done. All right, 5 CIS 300 degrees. Well, again, the main thing that I need to be able to do is come up with values for sine and cosine. Because all I'm going to do for x and y, and I'll give myself some more space this time, is take 5 cosine 300 degrees and 5 sine 300 degrees. So 300 degrees is going to be over in quadrant 4. All right, so here's 300 degrees. Now in terms of a reference angle, reference angles are always connected to the x-axis, which means my reference angle is going to be just slightly more than 300. So in order to find that reference angle right here, I'm going to have to do 360 minus 300 to get 60 degrees. Now, because I know it's 60 degrees, I can determine then what the values of sine and cosine are based off of a 60 degree angle measure. So opposite the 60 degree angle is going to be the middle sized value, which is root 3 over 2, and opposite the 30 degree angle there would be 1/2. In terms of positives and negatives, I'm in quadrant 4, so all students take calculus, which means cosine values are positive. So that would mean that value right there, which is a sine, would need to be negative root 3 over 2. Now, to work these out, 5 cosine of 300 is determined to be 1/2. So that gives me 5/2. 5 sine 300 degrees would be 5 times negative root 3 over 2, which would be negative 5 root 3 over 2. So my value z could then be written as 5/2 minus, actually I'll put the I first here. Sometimes Sometimes you choose to put it before, sometimes you put it after. As long as it's in there, it doesn't make a whole lot of difference. I feel like it's more visible sometimes before. It doesn't really matter. Okay, operations on complex numbers. Addition and subtraction. To add or subtract complex numbers, this is most easily performed in rectangular form, and you simply add and subtract the real and imaginary parts separately. So for instance, here are two imaginary numbers that I want to add together. So all I need to do is take the real parts and group them, the imaginary parts and group them. So 2 minus 8 is negative 6, negative 3i plus 2i is minus I, and we're done. For another example, 6i minus 1 minus I. So this is effectively 6i minus 1 plus I. So this becomes negative 1 plus 7i. You just add the real parts and the imaginary parts separately. Multiplication. Multiplication on complex numbers in rectangular form is much more complex. You have to FOIL the terms of the numbers and then simplify. However, in trigonometric form, you can use the following rule. So you have one number provided in trig form, r1 cis theta 1. You're going to multiply that by another value in trigonometric form, r2 cis theta 2. The product is the product of the radiuses, or radii, I'd suppose, cis, and then the sum of the angle measures, which is much easier than doing the FOIL process from the rectangular form. So for instance, I've got these two written in trigonometric form. So all I need to do is 3 times negative 2 cis 60 plus 15. So this becomes negative 6 cis 75 degrees. If you need to simplify it, go ahead and simplify it. And you would if your angle measure is outside of the bounds of 0 to 360 and stuff like that. But in general, you're done. Let's try it from rectangular form. Now, in rectangular form, I normally would have to FOIL this. So to FOIL it, what would happen is I would take 2 times the square root of 3, 2 times negative I, negative 2i times root 3, and negative 2i times negative I. Multiply that all out, add up the like terms, and simplify. So it's a multi-step process. It's not the easiest thing to do in the world. So what we're going to do instead is convert these into trigonometric form and then multiply. We're going to answer our final answer in trig form. So in order to do that, what I'm going to do initially is to first just set up the problem so that it's a little bit easier to do. In order to do that, I need to factor out from this group. I'm going to factor out 2 square root of 2. And out of this group, I'm going to factor out just 2. Now, why am I choosing that? Well, I'll show you. So, when you factor out 2 square root of 2 from the first set of parentheses, you're effectively going to divide each term by that. Okay, and same for the next set of parentheses. So I'd have 2 times root 3 over 2 minus 1/2 I. And it might be more visible at this point as to why I've chosen the second set of parentheses to factor out a 2. Because you can see root 3 over 2 and 1/2. Those are common values of our angle measures for sine and cosine. That's what I'm looking for here. In the first set of parentheses, if you'll notice, the 2's would cancel, and that would leave me 1 over root 2, which is the same thing as square root of 2 over 2, minus square root of 2 over 2 times I. And then I'm going to leave this alone. This is actually all ready to go. So then basically what we need to do, this right here is the radius. And I could have found that radius by using r equals the square root of x squared plus y squared. I just saw it a little bit differently in this case. You can certainly go back to those formulas. Absolutely. No problem at all. The angle measure, let's see what angle measure we should use. So if you'll notice, I'm looking for a root 2 for cosine and sine, but I would need the sine value to be negative. So let's see what quadrant we're in first. So cosine is positive and sine is negative. So all students take calculus. So cosine is positive, sine is negative. The only possibility there would be quadrant 4. So in quadrant 4, I'm looking for something where the cosine is positive root 2 over 2, sine is negative root 2 over 2. So this would be CIS 315 degrees. For the other one, again, let's start off by getting the right quadrant. So I have cosine positive and sine negative. So again, I'm in quadrant 4. Cosine is root 3 over 2. Sine is negative 1/2. So this is 330 degrees. So this is going to be times 2 CIS 330 degrees. You're probably thinking at this point, it's probably easier just to do the FOIL. And you may have a point. This is just to show that you absolutely could do it this way. So this would be, I multiply my radii, so 4 root 2, and add the angle measures. So 645 degrees. Now, the only problem with that is that 645 is outside of my range of 0 to 360. So I want to get something that's coterminal to that. So if I take 645 and subtract 360, that gives me 285 degrees. So this is the same as 4 root 2 CIS 285 degrees. And we'll leave our answer in trig form, so at this point we're done with that particular problem. Division. So we're going through all the different operations here. We've done addition, subtraction, multiplication. The next up is division. Division can be performed in a similar fashion. So when you're dividing two complex numbers in trig form, you divide their radii and subtract their angle measures. So for example, let's divide these values and we'll give our answer in rectangular form. So in order to do that, we'll take the two radiuses that are provided. So 10 divided by negative 5, that is negative 2. Now, the angle measure we find by subtracting. So 300 minus 60 is 240. We already have our answer. We've divided and we have our answer in trigonometric form, although it's asking here to provide the answer in rectangular form. So it wants us to convert. So basically we need to figure out what sine and cosine are for 240 degrees. So it would be negative 2 sine, whoops, I'm sorry, for x it would be the cosine, 240 degrees, and for y it would be negative 2 sine 240 degrees. And since I have the unit circle handy, I'll just use it. Here's 240 degrees. There's my cosine and my sine. So cosine is negative 1/2. Whoops. Let me do this. Scooch it over a little bit. So this would be negative 2 times the cosine of 240, which is negative 1/2, and negative 2 times sine of 240, which is negative root 3 over 2. So this is going to be 1, and this is going to be root 3. So that gives me an answer, which is 1 plus I square root of 3. Now, this particular problem, there's actually multiple ways we could have gone about this. So if you'll notice, I have this negative right here for my radius, and technically in trig you're not supposed to have negative numbers for your radiuses or your radii, if I'll be careful there. And we should have probably taken care of that ahead of time. It all came out in the end just fine because we were converting to rectangular form. But if we were going to stop at this point in trigonometric form, we wouldn't have been quite done yet, because we would have, you know, a negative radius, and so we would have needed to adjust for that. So just kind of keep that in mind. So the idea, let me show you. I can actually show you on the unit circle, I think. So assume this circle here is radius 2. Okay, so if it's radius 2, here's my vector right there. All right, that would 240 degrees. But if it has a radius of negative 2, it goes in the opposite direction, which would go this way. And so that's effectively what's happened, is the point that we gave was this point right here. This would have been, you know, positive 1/2 plus, or I'm sorry, not 1/2, but 2 times 1/2. So it would have been 2, nope, not 2. Just 1. 2 times 1/2 is 1. 1 plus I times the square root of 3, which is where we ended up. So changing it into rectangular form actually adjusted for that. But I just wanted to point it out because it is a little bit strange in that particular setup that we had a negative radius. It is possible, but we generally do have to adjust for it.